Okay, this is 3.4, the water park, and this is a solidify understanding task. So today we're going to take a look at graphs and talk about the important things we need to show on a graph so we can communicate appropriately. And we're going to also be introducing things like, we're going to solve simultaneous equations graphically today. We're also going to see an inequality for the first time. Some things that we're going to go into in the next couple chapters. So it's going to be a lot of fun, and this is really a cool activity. So here's the situation. Allie and Dane work at a water park and have to drain the water at the end of each month for the ride they supervise. Each uses a pump to remove the water from the small pool at the bottom of their ride. The graph below represents the amount of water in Allie's pool, A of x, so that would be this blue graph right here. And then and Dane's pool, D of x, over time. And Dane is this darker blue graph right here. Okay, so let's look at part 1, number 1. Make as many observations as possible with the information given in the graph above. Okay, now they've done a pretty good job with this graph right here. They've shown us everything we really need to know, basically. Let's think about this. There's hash marks, and they are not scaled, so we would assume that each hash mark represents 1 unit. And Allie's graph is represented with A of x, A in terms of x, and Dane's graph is represented with a D of x. All right, and there's a couple things we could add to this graph, but we'll get there in a second. Let's just talk about right now what this tells us right now. So A of x, well, let's think about it now. A of x, well, Allie's pool, look, the amount of water in gallons. Allie's pool has 1, 2, 3, 4, 5, 6, 7 gallons. And at first I was thinking, man, that's not a lot of water for a pool at a water park. But then I read from the small pool at the bottom of their ride. So I'm thinking, okay, maybe at the bottom of the ride, there's a small pool that contains some of the water in the entire pool where they do the draining and such from. Okay, so maybe that's reasonable. And so it looks to me like the horizontal axis for our independent variable is time in minutes. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So it takes 20 minutes for Allie's pool to drain. And then I'm thinking 7 gallons in 20 minutes? That's pretty slow. Something's missing here. But let's talk about what we do know. So, and we're going to do that with the features of functions. So first of all, is A of x, this blue graph right here, is that the graph of a function? And would you guys all agree that that would pass the vertical line test, which implies every input has one and only one output? So yeah, it's a function. And the domain. Well, based upon this graph, I'd say the domain is in a closed interval from x equals 0. And we counted that earlier, wasn't that 20? So in interval notation, I'm going to go bracket, bracket. And my left endpoint is 0. And x can equal 0. And my right input is 20. And x can equal 20, and that's why we had to use brackets on both endpoints right there. So those are all the x values according to Allie's graph right here. Now the range, well, the minimum y value would be a 0, and that's the y coordinate at this point right here. And we go all the way up to, again, 1, 2, 3, 4, 5, 6, 7. So it looks like the range is all y in the closed interval. So again, bracket, bracket, from, and my lower y bound is 0, and my upper y bound is a 7. Okay, now extrema. Well, this blue graph does have a maximum and a minimum. So let's write those in ordered pairs. Okay, so the maximum value would be the ordered pair that represents the y-intercept here, and x equals 0, y equals 7. And the minimum value is this x-intercept down here, which would be x equals 20 and y equals 0. Also notice, at the y-intercept, x always equals 0, and at the x-intercept, y always equals 0. That's going to help you out. Now, f is increasing on. Well, is Allie's function ever increasing? No, it's decreasing within its entire domain. So I'm going to say the empty set. F is decreasing on. Well, Allie's graph is decreasing within its entire domain. So all I need to do is rewrite the domain we wrote above. X is in the closed interval from 0 to 20. There you go. And the y-intercept is the coordinates of this max right here, 0, 7. And the x-intercept is the coordinates of the min right here, which was 20, 0. And there you go. So there's all the features. That's everything I can tell right here. Okay. So let's take a look at the next part right here. Oh, let's talk about d of x. Let's talk about Dane's graph first. Okay, because we're going to compare these two functions. So how about some features of Dane's function right here? And would you guys all agree that Dane's function also passes the vertical line test? Therefore, every input has one and only one output, so it is a function. And Dane's function goes from x equals 0 all the way to x equals, and that would be 21, 22, 23, 24. So I'm going to say the domain is all x in the closed interval, bracket, bracket, from 0 to 24. And what's the range? Well, that's all y in the closed interval, bracket, bracket, and the minimum y value of Dane's graph would be the y coordinate of this point right there, which is 0. And we go all the way up to 1, 2, 3, 4, 5, 6. 0 to 6. And extrema. Well, Dane's graph has a maximum value, and that's the y-intercept, 0, 6. And it has a minimum value, and that would be the x-intercept here, which is going to be 24, 0. And f is increasing on. Well, again, Dane's graph is never increasing. Empty set. F is decreasing on, and Dane's graph is decreasing within its entire domain. So we're just going to rewrite the domain for Dane's graph, which is x is in the closed interval from 0 to 24, just like you see above right there. And the y-intercept was the maximum output of Dane's graph, 0, 6. And the x-intercept is the minimum value of Dane's graph, represented by this ordered pair, which is 24, 0. And don't forget, at the y-intercept, x is always 0, and at the x-intercept, your y is always 0. All right, pretty cool. So Dane figured out that the pump he uses drains water at a rate of 1,000 gallons per minute and takes 24 minutes to drain. Well, I agree with the 24 minutes, 20, 21, 22, 23, 24. But we just said the maximum amount of water in that small pool for Dane's pool was 6 gallons, and we're draining 1,000 gallons per minute. So there's something wrong with this 7 I have right here. So with Dane's information, we can get a more accurate graph. We'd better get rid of that 7 and think about this. Now, if it takes, well, let's say Dane's pool is draining at 1,000 gallons per minute, and it takes 24 minutes to drain. Wouldn't it make this y value right here 24,000? All right. Very cool. Okay, so, and let's just keep going here. So let's think about this. Let me double check the hash marks now. Okay, so let's see if we go by 4,000, if this is going to work. 4,000, 8,000, 12,000, 16,000, 20,000, 24,000, and 28,000. There we go. So it looks to me like Dane's pool is holding 24,000 gallons of water, and Allie's pool holds 28,000 gallons of water. It looks like Dane's pool took 24 minutes to drain, and Allie's pool took 20 minutes to drain. Okay, so number 2, write an equation to represent the draining of Dane's pool d of x. What does each part of the equation mean? Well, this is linear, okay? So let's come up, and we do have a y-intercept. So could we use slope-intercept here? Y equals mx plus b. So we're going to go, and let's use d of x for y. So d of x equals, and what's the slope right here? Well, Dane just told us that the pool is draining at 1,000 gallons per minute, and that's what a slope is, a rate. So I'm going to say the slope is negative 1,000. And then plus b, the y-intercept, plus 24,000. And there's the equation. What does each part of the equation mean? Well, you've got your slope of negative 1,000, and you've got your y-intercept of 24,000. So the slope of negative 1,000 implies Dane's pool is draining at 1,000 gallons per minute. 1,000 gallons drain every minute. And b equals 24,000 implies Dane's pool, when it was full, held 24,000 gallons of water. When the pool was full, it held 24,000 gallons of water. Very cool. All right. Number 3, based on this new information, correctly label the graph above. Well, again, look at how they told us the horizontal axis is measuring time in minutes, okay, and the vertical axis is measuring amount of water in gallons. And we figured out what each hash mark is worth, both on the horizontal and the vertical axis. So really, the only thing more that I could probably add is let's label the horizontal axis with an x. All right, and we might label this x-intercept of 24 right there as well. And we can't really label the vertical axis because there's 2 functions on this graph, one of them a of x and the other d of x. So we're not going to label the vertical axis here. So that's a great graph now, and with that graph we could use this graph the way it is labeled to answer any question. That's a great model. All right, so for what values of x make sense in this situation? Use interval notation to write the domain of the amount of water in Dane's pool. Now, we already did it with our functions, but let's do it one more time right here then. So Dane's pool is draining from 0 minutes to 24 minutes. So that's going to be the close interval from 0 to 24. So close interval, so I have to go bracket, bracket, and my left endpoint is 0. And my right endpoint is 24 on the x-axis. Okay, cool. Now, number 5, determine the range or output values that make sense in this situation. Use interval notation to write the range of the amount of water in Dane's pool. So those are all my y values here, or outputs, the vertical axis right here. And this is going to be the closed interval. When Dane's pool is empty, it has 0 gallons. And when Dane's pool is full, it holds 24,000 gallons. So we're going to have y in the closed interval, bracket, bracket, from 0 to 24,000. Nice. Okay, number 6. Write the equation used to represent the draining of Allie's pool, a of x. Okay, let's start with that. So Allie didn't tell us the rate at which her pool was draining, so we're going to have to figure out the slope another way. All right, well, slope is rise over run, and I'm going to use the 2 points that I know about right now. So I'm going to say the slope is, and Allie's pool is rising negative 28,000, and it is running 20. All right, so let's get out our calculator and punch that out. Make sure we get this right. Negative 28,000, negative 28,000 divided by 20, and I am getting negative 1,400. So the slope of Allie's graph right here is negative 1,400, or that means now the pool is dropping 1,400 gallons every minute. Okay, that's quite the drain there, actually. Okay, so y equals mx plus b. Now let's write this in terms of a of x to represent the function for Allie's pool. A of x equals, and my slope is negative 1,400, negative 1,400 times x, plus the y-intercept b, and the y-intercept of Allie's pool is 28,000, so plus 28,000. Okay, and then using interval notation, state the domain and range for the function a of x, as well as the domain and range of the situation, and compare the two domains by describing the constraints made by the situation. So I decided to go ahead and put these together so we can compare. So the domain of a of x implies, well, again, a of x is going from x equals 0 to 20. All right. And the range of a, well, let's go to the domain of dx now. I think I did this domain now. And Dane's pool went from 0 to 24. Yeah. Now let's do the range. So the range of a of x, well, that's my y values, and we begin at 0, and we go up to Allie's pool, 28,000. And the range of Dane's pool would be from 0 to 24,000. There we go. Now, what does this mean? Okay, so, well, it takes 20 minutes for, what, 28,000 gallons to drain from Allie's pool, and it takes 0 to 24 minutes for 24,000 gallons of water to drain from Dane's pool. Nicely done. Okay. So, number 7. When is a of x equal to d of x? All right. And you all, when we get to module 5, we're going to be solving systems of equations. And the first way we're going to do that is we're going to solve them graphically, which that is essentially what they are asking us to do right here. When is a of x equal to d of x? So let's remember our two functions right there. And now in module 4, we're actually going to do stuff like set this expression equal to this expression and solve. But today they want us to do this graphically. So I'm going to look at the graph, and when is a of x equal to d of x? Well, that would be, there's the point where they intersect, and time is my x-axis, so it'd be that x value right there. Let's count them carefully. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in 10 minutes, the two pools will have the same amount of water. So x equals 10 minutes. And what does that mean? After 10 minutes of draining, both pools will contain the same amount of water. Right on. Okay, find a of 5. All right, function notation, a of 5. So 1, 2, 3, 4, 5. There's x equals 5. And I'll draw a vertical line right there to go up to Allie's graph, and I'm right here. Now, a of 5 would be the y value of this point right here. So, what's that y value right there? Well, it looks like we're going to have to approximate. Well, if this is 20,000 and this is 24,000, that looks like it would be approximately 21,000. So, after a of 5, that 5 means 5 minutes of draining, Allie's pool will contain about 21,000 gallons of water. Okay, let's see. Great. Number 9. If d of x equals 2,000, so 2,000 would be my output, and remember, every hash mark is 4,000, so 2,000, like y equals 2,000 would be the horizontal line right here. Right there. So if d of x equals 2,000, then x equals, well, let's look at Dane's graph when it's at 2,000. Right there at that point, Okay, and what's the x value at that point? Looks like that x value is a 22. X equals 22. So that means in 22 minutes, Dane's pool will have 2,000 gallons of water left. After 22 minutes of draining, Dane's pool will contain about 2,000 gallons of water. Nice. And when is A of x greater than D of x? Our first inequality right here. So now we need to look at these two graphs and determine when is A of x higher than D of x on the graph. Well, they intersect right there. All right. So this is the branch of Allie's function that is greater than Dane's function right there. Okay. So this interval. So when I need to know the x interval from this point to this point. And greater than, that means we're going to have to do this as a half open interval. So that's the 10 right there. So notice I'm going to start at x equals 0 and x can equal 0. That's why this is a bracket. To how far? And that was 10 right there. And we have to have a parenthesis on the right because in 10 minutes the pools are going to have the same amount of water, and we want to know when does Allie's pool have more gallons than Dane's pool right there. So that's the half open interval from 0 to 10 where x cannot equal 10. And what does this mean? Well, let me see. Blank until the pools have been draining for, okay, so A of x is going to be greater than D of x until the pools have been draining for how many minutes? 10 minutes. Beautiful. Oh my. That was it. So you guys now do a great job on the 3.4 Ready, Set, Go. And let me know if you have any questions. All right. I hope you guys enjoyed this video as much as I enjoyed it. Have a great day.